Hey everyone, welcome to this video in which I will be going over the actor-partner interdependence model with indistinguishable dyads. In a previous video, I have gone over the actor-partner interdependence model with distinguishable dyads, and so this one will focus on indistinguishable dyads. The difference between distinguishable and indistinguishable dyads is that there is a variable within your data set from which you can theoretically differentiate partner one from partner two in distinguishable dyads. And that's going to be a variable that is theoretically related to your research question. So for example, gender is often used as a distinguishable variable in heterosexual couples, for example. Parent-child, that the role of being a parent and being a child is a distinguishable or a distinguishing variable. But oftentimes we're going to work with dyads in which there's not a theoretically driven or theoretically informed rationale for who is partner one and who is partner two. Instead, the assignment of partner one and partner two is going to be completely arbitrary. And so we can run an actor-partner interdependence model with these indistinguishable dyads, but we just need to make a few additional constraints. So I will demonstrate that within the Mplus software that you see here. And so this is a data set where we have a set of identical twins. So we have a set of identical female and male twins all within the same sample. And we are going to be looking at the influence of family support and on positive affect among indistinguishable twin dyads. And so what you'll see here is here's our 8 variables, and then we're only going to be using 4 of them. So we're just going to run, again, the basic actor-partner interdependence model. We have a missing data command because there are some missing data cases or some missing data values in this data set where we don't have 100% complete data, so we need to specify that. And if we don't specify the -999 here, Mplus is going to read that -999 as an actual value that's possible. And not surprisingly, that's going to throw your results all out of whack. All right. And so, oops. And so what we are going to do now is estimate the actor-partner interdependence model with indistinguishable dyad. So what you will see here is actually the ISAT model. This is the test for distinguishability that you may have heard about Dave Kenny and colleagues talk about, as well as Tom Lederman and colleagues discuss. And this is a way to theoretically distinguish dyad members to see if those theoretical propositions empirically hold. And so we do that with both indistinguishable and distinguishable dyads. But with indistinguishable dyads, you also keep these constraints in the model. And so that's why I'm changing these with statements to on statements. And so briefly, we have T2 positive affect on T1 support. And so many of you might think that that's time 1 and time 2. That is actually, in this case, not necessarily true. And instead, I have labeled it as T2 for twin 2 and T1 for twin 1. All right, so T stands for twin and not time in this analysis. And so we have twin 1's positive affect on twin 1 support. So we could actually probably label this more effectively. We can do P1 here. And so we also have twin 1's positive affect being regressed onto twin 2 support. And so that is going to be a partner effect as well. And then you have your actor effects here, where twin 2 is regressed on twin 2 and twin 1 is regressed on twin 1. All right, so remember, in the actor-partner interdependence model, we predict our own outcomes. So the independent variable for one dyad member predicts the outcome for one dyad member, and that's the actor effects. indicated here. And then we also are testing whether or not dyad member one's, the levels of dyad member one independent variable accounts for variation in dyad member two's dependent variable. And that's what we call a partner effect. And so P1 stands for partner effect 1, and P2 stands for partner effect 2. And then A2 stands for actor effect 1 and actor effect 2, respectively. All right. And so this is a way to, again, to test whether or not people are distinguishable. But also if you're working with indistinguishable dyads, you actually have to include these constraints in the model, because we're fundamentally assuming that assignment is arbitrary, okay? And so we have two partner effects here, whoops. And what we're gonna do is we need to constrain them to be equal, all right? So we're taking P1 and P2 and we're saying you are exactly the same. And we are gonna do the exact same thing with actor effects. And so in Mplus, if you're using just a regular model, this differs a little bit from multi-group models, but for just using a single group model, if you add these constraints, these parentheses, these labels at the end of a line of code, that tells Mplus that this pathway right here is called P1, all right? And so what we're gonna do is constrain these partner effects to be equal. So twin one's influence on twin two is exactly the same as twin two's influence on twin one. Likewise, we're going to do the exact same thing with our actor effects, because again, if we're assigning them arbitrarily and randomly, we are fundamentally assuming that the effects are exactly the same. And so also in the with indistinguishable dyads that you don't necessarily do with distinguishable dyads is you constrain the means to equality. So these we will constrain the means, or they're called intercepts as well. So you will see both in the Mplus output. So for twin one, their mean on positive affect is constrained to be equal to twin one's level or mean score on positive affect, just as twin one and twin two's levels of support are constrained to equality. All right. And so brackets in Mplus, that indicates a mean. All right. So if you put brackets around something, then you're telling Mplus that this is a mean, or this is perhaps an intercept. And if I had like C1 here, just for an example, then Mplus knows that this path is called C1, but it is, since there is another C1, so we'll call it D1. Since it's called D1, and there's no other path called D1, it's going to freely estimate that path. And that value, this label that you see, won't really do anything to the results. So you have to be sure that your labels perfectly match. Otherwise, Mplus is not going to constrain your effects to be equal. Or perhaps you might constrain the wrong effects to be equal. You might accidentally constrain an actor effect to be congruent or equal to a partner effect, and you don't necessarily want that in your analyses, at least at this point. So be really, really careful around your labeling of the values. All right, and so moving on to variances. And so just as we assume that the means and the regression coefficients are the same across twin members, we're also going to assume those variances, or perhaps those residual variances, are also going to be identical across the identical twins. Again, that also stems from the assumption that since assignment is arbitrary, there should be exactly equal effects across both dyad members. So here are your covariances. So your twin one support correlated with your twin two support, and your twin one's positive affect correlated with twin two's positive affect. Down here, you don't necessarily need this, but this is pretty much standard procedure in my analyses, is to obtain the scatter plots and the histograms for these variables, as well as identify potential outliers, but we will not go through those processes in this video. We will also look at the output, which we want the sample statistics, means, variances, skewness, kurtosis, things of that nature. We want the residual, which again won't probably give us much usable information, at least in this analysis. But again, it is one of those defaults that I use. We also want standardized output as well as modification indices, and we want confidence intervals around our estimates. So we can go ahead and we can run this analysis. Hopefully Mplus will like it. It does. And so you can scroll down. For the purposes of this demonstration, we can ignore this warning, but if this was more for substantive conclusions or for substantive paper, you would want to be wary that your 15 variables or 15 cases got deleted, and this is where you want to include a FIML statement. So we have 383 total twins. So we have a couple unmatched dyads, but I think the full sample is 398. So 383 plus 15 gives us our full sample. So we'll scroll down. We have our covariance coverage, our means, and our standard deviations, our variances, min, max, skewness, kurtosis, and other descriptive pieces of information that you would report in a manuscript. So scrolling down in the distinguishable variable actor-partner interdependence model, it is what's called a saturated model. So we are freely estimating the means, the variances, and the covariances among all dyad members. All right. But again, the purpose of the distinguishable dyad actor-partner interdependence model is to constrain those to be equal across dyad members because assignment is arbitrary and random. And so we actually want this test, which is one of the tests for distinguishability. We want this to be non-significant. Because if this is significant, that tells us that constraining the means, the variances, and the covariances, or the actor and partner effects, to be equal significantly harms the model data fit. And so that tells us that at least one of those parameters in there, perhaps we don't know which one, but at least one, there are significant differences across, in our case, the twin pairs. And so that tells us that they're not completely indistinguishable. All right, that tells us that there's potentially problems there, and our assumption of indistinguishability isn't met. And so we need to go take a look at why that is, what parameter might be off, and that's where you investigate them one by one, where you test each individual parameter one at a time to see which parameter is significant. Right. And so the chi-square test is generally the test that you would look at. Within the measurement and variance literature, people talk about a delta CFI. People have also talked, although less frequently, around a delta RMSEA. A delta CFI value of 0.01 or less indicates that there is not significant measurement differences, and that constraining the effects, the actor and partner and means, variances, and covariances doesn't significantly harm the model. So if we had a 0.992 here, that would still be within the realm of saying there is no harm done to our model by constraining all the effects to be equal across dyad member. And so we'll scroll down, and this is our unstandardized output. And as you can see, we have our partner effect here and our partner effect here, and they are identical. They are both 0.195. Likewise, we have identical actor effects of 0.14 or 138 rounded up. And so you'll see the standard errors are the same, the estimates are the same, the p-value is the same, everything is identical. All right. And then we also have our covariances. Again, these are in the metric of the raw variables. And so unless you perhaps standardize them before the analysis, these are only somewhat informative, or where the metric doesn't really give a whole lot of meaning to the substantive interpretation, unless perhaps your measures are also meaningful. So, a 1 to 5 scale on support or positive affect, that inherently doesn't have a whole lot of meaning out in the world, but there are other variables, such as like percentage of time talking. Perhaps you're doing an observational study that might actually be a little bit more meaningful. And so using the raw metric, when you have a meaningful scale on your variables, and using your unstandardized results tends to be the preferred way. But if you're just creating kind of using scales where the metric isn't meaningful, I tend to go with standardized, although I do report both. And as you can see here, the means are exactly the same. We have the intercepts are exactly the same. So we have the means on the independent variables, and we have the intercepts on the dependent variables. We also have our variances on the IVs, and we have our residual variances on the DVs. All of them are identical, right? So essentially what this tells us, it tells us the magnitude of the effects, but it also tells us we coded things correctly because all the parameters that are supposed to be the same are the same within this model. So that's a nice way to check your work in case you're potentially worried about misspecifying or having a problem in your syntax. So we can scroll down to the standardized, and we have a significant effects just as above, and this is a 1 standard deviation increase in support from twin 1 to twin 2, or twin 1's levels of support leads to a 0.15 standard deviation increase in twin 2's positive affect. Likewise, for the actor effect, we have twin 2's support, a 1 standard deviation unit and increase in that has a 0.11 standard deviation increase in their own levels of positive affect. And so what you can see here is that the actor and partner effects are actually relatively similar in magnitude, and we can actually go back and empirically test whether or not they're identical or not. Then we're getting into dyadic patterns, and I can show that in another video. But for right now, just knowing the interpretation of the actor and partner effects in a standardized metric is more than sufficient. And down here, we have our R squared. So even if you are interested in unstandardized effects only because you have meaningful metrics, it's always helpful to request the standardized metrics so you can get your R squared value, because this will not come with your unstandardized output. All right. And then down here, we have our confidence intervals for standardized down here and unstandardized up here. And then we have our residual output. And so here, since we do have, we have a good fitting model above, so I don't anticipate seeing anything really all that meaningful down below. But essentially what I do is I look at the residuals for correlations to see whether or not my parameters are being overestimated or underestimated. So this little guy right here, this tells us the relationship between T1 support and T1 positive affect is overestimated by about 0.05. And so we can go down here to the next box in the standardized residuals for the covariances, and we can see whether or not that is statistically significant. And these are z-scores, so the critical value is 1.96. And so as you can see, that is not significant. So that tells us even though there's a little bit of a mismatch between our expected value and our observed value, it's not all that significant. It's not all that important. And it's probably not wreaking havoc in our model. Likewise here, we have a value of negative 1.39, which means this relationship between twin one support and twin one support, so it means that the variance is underestimated based on what the model would have expected. And so that is something to perhaps think about. But since again the z value is not greater than 1.96, that's not something I'm really going to get concerned about. I tend to only really get concerned when there's standardized z-scores or standardized residuals that stick out kind of like a sore thumb. So when I have, if I have a bunch of ones, a few twos, and I have a 7, that tells me that there's a problem or a misspecification within my model. But here we are in the all clear. Nothing really sticks out. Nothing is statistically significant. And I kind of knew that going in based on the chi-square value, based on the CFI. If all of those tend to be really, really, really good, 0.98, 0.99, chi-square is non-significant, that tells us in some way that our residuals are most likely going to be okay, but there's not a perfect correlation. You can have a really, really good model up top, but you can also have a few parameters that are way overestimated or way underestimated down below. And so to me, it is always best to take a gestalt approach when evaluating model data fit. And so if I were to report this in a manuscript, I would talk about the global fit indices up above, and I would also talk about these are what's called local fit indices. And so I can say with more confidence that our model is correctly specified, and we don't have any potential problems in our model as it is. Hopefully this was helpful in walking you through the actor-partner interdependence model with indistinguishable dyads. I will continue to create these videos and expand them to mediation moderation for indistinguishable and distinguishable dyads alike.